Every year, our institute, iSEE, has been organizing a congress focusing on a critical sustainability challenge that we see as emerging and trying to bring together multidisciplinary minds from across our campus as well as other institutions around the world, often to share the latest science on the topic and to showcase the efforts that are there and the gaps that need to be addressed in order to be able to fully find solutions to these complex problems. So we're pleased this year to host our 9th Congress, which is focusing on addressing crises of planetary scale, lessons from pandemics and climate change. And as you all know, both the pandemic and climate change are the most pressing challenges that really threaten our human existence, and it's important to look at interdisciplinary approaches and global cooperation in order to find innovative solutions. So we're happy to do this, and I'd like to thank our sponsors, in particular our founding benefactor for our institute, the Alvin H. Baum Family Fund, led by Joel Friedman and Loretta Namowick, who couldn't be here today, but they have supported iSEE events over the past 9 years. Our Congress has also received funding from the Center for Global Studies through their grant from the U.S. Department of Education Title VI Natural Resource Center grant in Global Studies, and we really appreciate their support. I would now like to ask our Chancellor, Robert Jones, to deliver a few opening remarks. Chancellor Jones is a crop physiologist with expertise in agronomy and plant genetics, and with decades of research in the Midwest. He knows very well about the effects of climate change and what it means to future generations and not just for agriculture. He has shown a passion for the environment and chairs the Sustainability Council, which is a group of the top-level administrators who have put our campus on a path of carbon neutrality and to become a model of sustainability. Chancellor Jones has also provided the leadership to lead our campus safely through the COVID-19 pandemic and through developing an in-house saliva testing regimen that helped to keep our campus open very soon after the pandemic started. His support and encouragement has led to our scientists on campus making remarkable contributions to understanding and mitigating this deadly virus, and those contributions have had an impact both nationally and globally. We're really pleased to welcome him to provide some opening remarks to our Congress today. Chancellor Jones.
Well, thank you very much, Madhu, and let me start by saying good afternoon to each and every one of you. It is certainly a pleasure and an honor for me to welcome you all to this 9th annual iSEE Congress. As both the Chancellor of the University of Illinois at Urbana-Champaign, and as Madhu said, as a plant scientist who spent 35 of my 45-year career in higher education trying to elucidate the underlying mechanisms by which global climate change would disrupt the yield of cereal crops that are important to our ability to feed the world. So I hope you can understand then that this annual Congress is of particular academic as well as administrative importance to the responsibilities that I've had over the course of my career. So I want to start by congratulating Professor Khanna and all of the faculty and staff and everyone that's affiliated with our Institute of Sustainability, Energy, and the Environment for once again assembling this body of scholars, policymakers, and community and industry leaders around the theme of climate change and resiliency. It is absolutely fitting that the first Congress, the first one that is back in person, following the disruption of COVID-19 pandemic, that I can tell you that as a university and as an academic community, as Professor Khanna alluded to, I'm very proud of the way that we created an ecosystem around our faculty and their researchers that came together to create one of the most innovative COVID-19 tests in the world. And the way that our students responded during the first couple of years, particularly of that pandemic, doing all those most difficult things that we asked them to do. So I think we all would agree in this room that we're seeing in real time and unfortunately on a regular basis the devastating, life-threatening impact of climate change and the pandemic on the depletion of natural resources. And this, I think, is absolutely critical and vital that we address these interconnected threats and seek partnerships across disciplines and across the globe to tackle planetary-scale challenges like the emergence of infectious diseases and biodiversity loss, as well as climate change itself. And I think, as all of us know at this community, Professor, that one of the things we take great pride in, that we are the most multidisciplinary university, I think, on the planet. We don't just talk about it and admire what a wonderful thing it would be if we could do it. We live it each and every day. In addition to our 15 colleges, we're proud of the 10 multidisciplinary institute, and iSEE being one of those, as an example of how the challenges that we face in a society are so large and so daunting that no one scientist, no one institution, no one entity can solve them alone. Now it's my pleasure to introduce Will Saunders, who will give us an overview of the Congress and introduce tonight's keynote. Will is an assistant professor in preventive medicine and public health in the College of Veterinary Medicine. He is the director of the DVM and PhD joint degree program with 10 to 15 students at a time that are pursuing both degrees under his guidance. Will, I remember the good old days when I had 18 people in my laboratory, so I know you're having just so much fun each and every day. I'm jealous, actually. In addition to teaching and research, he is a clinical faculty member at the Wildlife Medical Clinic, assisting with case management and triage and rehabilitation of native wildlife species. Professor Sanders, thank you very much for being with us today, and thank you for all that you do for the University of Illinois, Urbana-Champaign, and the world. Will.
Thank you, Chancellor Jones. I'm excited to help kick off the Congress and to begin the conversation that will continue tomorrow all day. Emerging infectious disease and biodiversity loss and climate change are among the most critical planetary scale challenges humanity faces in the 21st century. The focus must shift from unilateral approaches, as we've talked about already, to coordinating among diverse stakeholders, addressing complex problems. My work is centered on this very idea of One Health, integrating across public health, veterinary medicine, and human medicine. And I'm excited to have this conversation happen at an even larger scale over the next day and a half, particularly including sustainability. iSEE Congress 2023 will highlight how interdisciplinary collaborations can help tackle the enormous challenge of coordinating global responses to crises of planetary scale. By bringing together experts from multiple disciplines, this symposium will foster further collaborations and provide a platform for community to engage in pressing concerns. So to prepare us for that, we have a wonderful invited speaker this evening, Professor Felicia Keesing. She's the David and Rosalie Rose Distinguished Professor of Science, Mathematics, and Computing at Bard College. Dr. Keesing is a biologist who studies the consequences of interactions among species, particularly in biodiversity declines. Her recent work focuses on how biodiversity influences the probability that humans and other animals will be exposed to infectious diseases. She has worked in Kenya since 1995, studying how the disappearance of elephants, giraffes, and other large mammals influences the way African savannas function. Dr. Keesing has published more than 100 papers with grant support from the National Geographic Society, the National Science Foundation, and the National Institutes of Health. Her work has been covered by the New York Times, the New Yorker, NPR, The Guardian, among others. And in 2020, she and her work were featured in BBC's Extinction, along with Sir David Attenborough. She served on the steering committee for the Vision and Change in Undergraduate Biology Education Conferences and was director of the project on science literacy funded by the Howard Hughes Medical Institute. In 2000, she received the U.S. Presidential Early Career Award for scientists and engineers. She's an elected fellow of both the Ecological Society of America and the American Association for the Advancement of Science. In 2022, she received the International Cosmos Prize. So Dr. Keesing's talk today will focus on, as you can see, crisis on planetary scale, lessons and opportunities. We'll explore climate change, biodiversity loss, and emerging diseases, what these issues have in common, and how they and their potential solutions are all interlinked. So with all of that behind us, I'm very excited to have you here, Dr. Keesing. You're a fantastic invited speaker. We're really excited to hear what you have to say this evening. So thank you.
Thank you all for being here, and thank you to Will for that wonderful introduction. Thanks to the organizers for hosting us all tonight and into tomorrow. I'm really honored to be here and delighted to have the chance to meet so many people already today, in fact. So we're here in this room, I think, instead of out there playing Frisbee on the quad, because we share a commitment, probably professional and maybe also personal, to addressing 3 daunting challenges. These graphics are from a report that came out just last month from the Intergovernmental Panel on Climate Change. And that report documented impacts that we've already observed, widespread and substantial impacts, as they say, on a number of different things. In the upper left, you can see impacts on agricultural crop production, and also impacts on human mental health, on displacement. There are impacts on infrastructure, et cetera. So we've observed a number of different effects already. And we've also can identify that some of those impacts, some of the climate change conditions that we've seen, as shown on the left, can be increasingly attributed to human influence. And so on the right, I don't know how well you can read that from the back, things like upper ocean acidification and increased heat events are all very strongly associated with human attribution, and then on the left are some that we're still sorting out. So these are some of the ones for which we have virtually certain connection to human influence, and then we go down to medium confidence. But essentially, for all of these physical climate conditions, we can attribute them with some confidence to having an impact caused by humans. Now, this report that came out also talked about what our future looks like, and it did that by putting it in the context of the past. This is the part that got the most attention from the media. This is looking at the extent to which the climate change that we've seen from 1900 to 2020 is going to change going forward. And so what they did here with this graphic is to calculate the average global temperature during these years relative to the long-term average from 1850 to 1900, and then this color coding represents the deviation from that longer-term average from the late 1800s. And the warmer the colors, the warmer the average was. And so this is not going to come as a surprise to any of you. It has been getting warmer and at an increasing rate, so that by 2020, the average global temperature was about 1.1 degrees warmer than it had been for that long-term average. So that was one half of this figure. The other half looked like this. This is what happens under different emission scenarios with the future projected climate change averages or global average temperatures under very high emission scenarios up till 2100, and then comparing them from high to very low emission scenarios. So under any of those scenarios, we're under substantial warming, but it's a question of how much and for how much longer that warming continues to increase. So that's climate change. The second daunting challenge we face is biodiversity loss, as you've already heard a little bit about. And so for this, I want to show you some figures from another intergovernmental panel. This, the Intergovernmental Panel on Biodiversity and Ecosystem Services, or IPBES, and this report came out in 2019. So here on the left is a graphic that shows examples of declines in nature, and you probably can't read all of this from the back, but the idea here is they're documenting just how extensive declines in nature have been over this period. So for example, up here they're saying that 47% of the extent of natural ecosystems has disappeared. And here they're saying that 25% of species that we know about on this planet are currently under threat of extinction. So it's documenting the extent of that. They also looked at how biodiversity loss threatens different groups, different taxonomic groups, and that's what's shown here. So this is looking at extinction risk in these different groups, shown here on the left with amphibians down here, bony fishes up at the top. And the color coding represents the proportion of members of that group that are at different risk of extinction. So the redder the colors, the graver the risk. And you can see that all of these groups have a significant chunk of their members that are at risk of extinction, but that risk isn't spread evenly across all of these groups. Some of the groups, particularly these ones down at the bottom, are of at greater risk than others. The report also cataloged the rate of change in biodiversity loss, and for this I'll show you this graphic, which is looking at the cumulative percent of species that have gone extinct in different groups. But before we look at these lines, I want you to see if you can see that gray shaded part down at the bottom. That's the expected percentage of species that should have gone extinct based on the prehistoric rate of extinction in the fossil record. So that's what we would have expected given what we call background rates of extinction due to all kinds of Earth processes, but not humans. And this is the rate that we've seen in amphibians, mammals, birds, reptiles, and fish since 1500, pretty much all attributable to human causes. So both in rate and in extent, we are in the midst of a huge mass extinction event. So the third crisis, as if that weren't enough, is emerging infectious diseases. And I don't think I need to say too much about that, given what we've all been through these past couple of years. It's still a total treat for me to be in a room in 3 dimensions with a group of people and to have the chance to go to a reception afterwards and talk to them. And I will never again treat that lightly. So I'm delighted to have you in person and not just on my screen. Now, of course, I'm going to say a little bit more about that. This is a snapshot from the Johns Hopkins University COVID-19 dashboard. I bet there are people in the room who watched this almost every day like I did. Yes, of course. So if you're not familiar with this, this was one of the best central repositories for all kinds of data about what the state of things for COVID, starting with the beginnings of the outbreak back in February and January and February. And it cataloged the number of cases shown here around the world. So if you can't read that in red, it's almost 700 million confirmed cases of COVID around the world. And then here, almost 7 million deaths. I took this screenshot last month. That's a pretty astonishing set of numbers globally. The good news, such as it is that this number is the number of vaccinations that have been given around the globe, and that's over 13 billion. So these are the fixed numbers as of the day of the screenshot, but these are the patterns through time for cases, for deaths, and for vaccinations. You can see all of these things have been waning recently, and in fact, waning so much that last month the Johns Hopkins University announced that, and that's what's in the yellow banner up here, that the dashboard was coming offline, and so it's actually, to my knowledge, no longer there. I believed them, I didn't go back and check, so they said they were taking it offline as of last month. So, but COVID-19 is, of course, not the only emerging infectious disease that we have. This is a figure from a paper that came out in 2008, 15 years ago, that shows the locations around the world where emerging infectious diseases of humans are thought to have originated, and there are hundreds of such diseases on this map. And the scientists who did this study also put those through time, the time of their emergence, and that's what this shows. And you can see some interesting patterns here, but I want to focus particularly on the increase in the number over these decades, right? So we've seen not just this global pandemic in terms of extent in the past 3 years, but also an increase in the rate over decades. So what we have are 3 grand challenges that are daunting enough. And I want to identify here some of the themes that have actually come up in the remarks before mine, which is that these all have something in common. They have a lot of things in common, and I want to highlight just a couple of them. The first of these is that they are all occurring at global scale, and of course that sort of sets the theme of the conference, crises occurring at planetary scale, and so that's very clear. They also all have anthropogenic causes. They're caused by things that we are doing, and we know what those things are, which is a secondary part of that and an important one. And then finally, I want to highlight that we also are well aware that for all 3 of these crises, their consequences are borne inequitably around the world. So some people bear the consequences of these crises much more than others do, and I'm going to come back to that theme later. But these 3 crises share something too that again has also been alluded to, and that is that they're actually interlinked. And so I want to just highlight a couple of those interlinkages now. I'm going to start by focusing on what we know about linkages between climate change and biodiversity loss. I showed you this figure before when I was just starting out talking about the IPCC report, and I was focusing on some of the observed impacts that we've seen up here, but I want to focus instead down here, which is in gray. This is the effect of climate change on biodiversity and ecosystems, and here they're separating terrestrial, freshwater, and ocean ecosystems and saying we have seen observed impacts on all of these as a result of human-caused climate change. I don't know if you can see, but there are little asterisks underneath each of these, and those asterisks are coded over here for the degree of our confidence that there are big impacts going on here, and all of these things are known with high confidence. Okay? I also showed you this figure when I was talking about this other intergovernmental panel, the biodiversity one, and I focused our attention over here, but over on the left, there are various kinds of direct drivers of the three different sort of sectors of biodiversity loss: terrestrial, freshwater, and marine. And I want to highlight here that one of those drivers is climate change here, and that is this here, this section right here in this sort of darker orange. So climate change is known to be a direct driver of a lot of biodiversity loss across all three sectors. So there's clearly an interface between climate change and biodiversity loss. Now let me just say briefly that we also know there are strong linkages between climate change and emerging infectious diseases. That's work done by people who are going to be here and on panels tomorrow, so I hope you'll get to hear a lot more about that. I'm just going to highlight one recent paper that was very interesting. This is a paper that looked at linkages between climate change and cross-species viral transmission risk. And the sort of essence of this paper is that species ranges are moving as the result of climate change. They're shifting, right? And that's putting species in contact with each other that haven't previously been shared the same areas. And so that results in contact zones between species that could actually share viruses. And so this is numeric index of the number of potential viral sharing events that could occur as the climate shifts and species ranges move with them. And that was work done. Kevin Olival, who's going to be here tomorrow, is one of the authors on this paper, along with Colin Carlson. So there are lots of other examples of relationships between climate change and emerging infectious diseases. I'm going to now move on to a final interlinkage here between biodiversity loss and emerging infectious diseases. This is something that I do a lot of work on. And here, the sort of underlying connection is driven by the fact that some species are more vulnerable to extinction than other species are. And the species that are more vulnerable to extinction tend to share certain kinds of traits. So here I'm going to give you sort of a big view from 30,000 feet of what those traits are. The species that are most vulnerable to extinction tend to have a small geographic range. They tend to have a long lifespan. They tend to mature late in their lives, and they tend to have relatively few offspring in each litter. Okay? Some of you have probably heard that before. These are pretty commonly known things. But let's look at this. This is a little bit more recent. This is what are the characteristics or the traits that are associated with the species that give us diseases. And here I'm going to be referring specifically to what are called zoonotic diseases. So what does this mean? Here I mean zoonotic diseases, which are diseases that are caused by pathogens that can be shared between humans and other vertebrate animals. And we've found fairly recently that the species that share zoonotic diseases with us also have a set of traits. And here's what they are. They tend to have a large geographic range. They tend to have a short lifespan. They tend to mature early in their lives and have a relatively larger number of species in each litter. So, not to beat this, but basically the species that have traits that make them most vulnerable to biodiversity loss have exactly the opposite traits of the species that tend to give us diseases. And conversely, the species that are most likely to give us diseases have traits that make them very unlikely to go extinct from biodiversity loss. So I'm going to show this to you again in a slightly different presentation, a little more data rich. This is from a paper that my colleague Rick Ostfeld and I published a couple of years ago. And what this is showing is what's called the red list status, or the conservation status of different species. I'll walk you through this with the arrow going this way for greater conservation concern. So species that are coded blue, green, or especially yellow are of greater conservation concern than species that are coded black or this sort of orangey color. All right. So how does this work? Well, let's start with this group. These are the carnivores. So I'm looking here just at groups of mammals, and we're starting with the group that includes only carnivores. So this is, lions, tigers, and bears, dogs, cats, weasels, etc. And so what we're going to start with is looking at the proportion of species in each group that are not known to host zoonotic viruses, so to share zoonotic viruses with us. So again, these are carnivore species that are not known hosts of zoonotic viruses. Okay? And in this group of non-host carnivores, just over 25% of them are of these greater conservation concern categories. Okay? So let's say 30% of these are of conservation concern. But now let's compare that to the species in this group that are known to host 1 or 2 zoonotic viruses. Well, then that proportion drops a little, right? The species that host 1 or 2 zoonotic viruses are less likely to be of conservation concern. But then we also have a category of hosts that we call superhosts, and those are the ones that host more than 3 or more zoonotic viruses, and they are even less likely to be threatened. Okay? So what I'm telling you is that the species that host zoonotic viruses are less vulnerable to biodiversity loss than the species that do not, but that's just for the carnivores, the members of this group. So let's see what it looks like when we look at other groups. This is a group called the Ceet artiodactyla. That's a mouthful, which basically contains most of the hoofed mammals that you would think of, sheep, goats, deer, antelope, giraffes, etc. And in this group, what do we see? Exactly the same pattern. The hosts and the superhosts are much less likely to be of conservation concern than the non-hosts are. Well, there's 2 groups. Let's keep adding. What about the bats, about which we hear so much? Well, they show a similar pattern. What about primates? They show the pattern to an extreme. And what about the rodents, the group that gives us the most zoonotic viruses of all by quite a lot? Not a single superhost is of conservation concern, and there are virtually none in the host category. Okay? Now, why did I pick these 5 groups? Because these 5 groups of mammals give vastly more zoonotic viruses than any other group. These are the big 5 that share with us from the mammal world. Okay. So I've shown you these 3 planetary-scale crises, and so far I've emphasized the scale and the fact that they're also interlinked. And what I'd like to do forward is sort of move to the theme of the conference, which is what are the lessons we might draw? What are some opportunities, particularly for people who are going to stick it out and be here for this conference and take advantage of the legendary multidisciplinarity of this campus, of which I am already a big fan? And then I'm going to end with a couple of caveats at the very last couple of slides of my talk. So let's think about lessons. Well, one of the daunting things about these crises is their scale. And of course, the fact that the problems are interlinked. So what are we supposed to do that? Well, I like to spin things, so I'm going to reframe the fact that the problems are interlinked by pointing out then that if we do this right, so are the solutions, right? So let's think of it that way. And I want to give you a couple of examples of interlinked solutions, or how we might think about them. Last year, the New York Times and a number of other news organizations published articles to something to this effect, that our response to climate change is missing something big, right? What was that? Well, what they were reporting on was a conference at which the 2 intergovernmental panels that I have already mentioned, the IPCC and the IPBES, had actually for the first time sat down together and had a conversation, right? Scientists from both sat down and had a conversation. And the New York Times was reporting on that conversation. And here's basically what the scientists that sat down and looked at both problems together had to say. They said previous policies have largely tackled climate change and biodiversity loss as 2 separate problems. But there are policies that could simultaneously address synergies between them while also considering their societal impacts, and that has an opportunity to maximize co-benefits and help meet the development aspirations of everyone. That sounds pretty good. right? I like the sound of that. And the article in the Times actually illustrated the concept with an example from one of the co-authors of this report that was from Senegal, where a community living on the coast of Senegal had worked to restore their mangrove ecosystems and also to adopt sustainable fisheries practices. And as a result, dolphins had returned to their waters and 20 species of fish had returned. They also had stabilized their shoreline, and the mangrove ecosystems were storing a lot more carbon than the eroded area that they had before. So an example of restoring for biodiversity and climate change that also had other co-benefits as well. Well, this is an example of restoration, and I don't want to stop with this one. Some of you may know that 2023 is the third year of what the UN calls the decade of ecosystem restoration. And there are examples of restoration projects around the world. I'm going to just say briefly about one of my favorites. This is an image from Mozambique, from a national park there called Gorongosa. Mozambique, as some of you may know, was devastated by a 28-year civil war that killed 1 million people and 95% of the wildlife in the country. But when the Civil War ended and the rangers were able to start protecting the boundaries of the national park again, wildlife just started turning up from no one was quite sure where. But they started coming back to this place that they recognized as being safer. And so that park has come back to extraordinary life for wildlife. Now, these zebras didn't come back on their own. These zebras are being shown being translocated from another part of Africa to this particular park, and they're being gently allowed to acclimate before their blinders come off. This is just one of thousands of restoration projects going on around the world. So I'll show you this image, and I know you can't see these little numbers that are here, but these aren't individual restoration sites. This is from a group called restore.org, and each of these represents dozens and in some cases hundreds of restoration sites that if you clicked on, you could continue to zoom in on and see restoration around the world. And I can guarantee this is at least an underestimate by a factor of 10 or 100. You know, there are a lot of restoration projects going on out there. And these restoration projects are often focused on restoring biodiversity, but virtually always also are storing carbon and reducing carbon loss. So that's an example of the scale, perhaps, of interlinked solutions around the world. I want to mention another interlinked solution, this one led by Professor Brian Allen, who's one of the organizers of the conference. I was a part of this project as well. This was a project in central Kenya where we looked at the consequences of integrating livestock and wildlife on the same properties. And I won't go into a lot of detail about this, although if you catch me at the reception, I would love to. But I would just say that what we found is that under some conditions, wildlife and livestock can actually live together to the benefit of biodiversity, but also to the benefit of human and, in fact, also wildlife health. It was a wonderful, encouraging story. Okay, so interlinked solutions matter. I want to switch, and that's one thing that we can learn from these last few years. I want to switch gears and think about how research can also make a difference. And here I want to focus on a few different studies, but I'm going to focus first on one that just came out last month in Nature. And this was a study on sort of reforestation in 3 tropical forest areas, vast tropical forest areas. And in a nutshell, what this study showed is that regrowing tropical forests are absorbing megatons of carbon. Okay? So what the researchers did, is they looked at tropical forests in the Amazon, in Borneo, and in Central Africa, and some parts of those forests are actually regrowing. Right? They're returning. And so they estimated if we allow those forests to continue to regrow, how much carbon would that store? And here's the good news, it's actually quite a lot, megatons. These are megatons of carbon. So this is somewhere around 100, around 30 megatons of carbon from areas that are already regrowing, right? So that's wonderful news. You might be able to tell from the scale here that there's more to come. You know, those green bars don't quite make it all the way to the end, and that's because they also calculated how much carbon had been lost from deforestation, and that's a little more sobering, right? So that's how much we've lost from deforestation and degradation, but this is how much is already coming back from areas that are already growing, and so there's a lot of potential to increase that regrowth in these different forest systems. Okay, another example of research making a difference. Here from UIUC, I love this example. This is from some scientists who basically figured out a way to monitor wildlife populations less invasively. And what they did was to figure out how to take a dung sample from, in this case, they focused on elephants, but you can take a dung sample from elephants and put it on what's called a DNA preservation card that can actually be, so that the DNA from the dung gets stored on a card that can be kept at room temperature and transported safely without chemicals beyond what's embedded in the papers on the card. That card can be brought back, and these researchers showed that you can actually extract the DNA at very high quality, so you get multiple high quality, full genome reads from the wildlife species that produced the dung. But also very interestingly, it also recorded the plants, arthropods, and microbes that were also in the dung. So for example, the plants that in this case, elephants had eaten, their genomic signatures were recorded in the dung. So it's really a pretty breathtaking technique, and this just came out a couple of months ago. So it's giving us a method for monitoring wildlife that allows us to do it much more simply and without the risk, the stress to the animals, and also without the stress to the researchers. If anyone's actually ever tried to dart an elephant, you might appreciate the scale of the challenge. Let me give you another example. This is also from UIUC. This just came out in Nature Chemistry last month. This is work, I'll say more about who did this work, from what departments they are. This is about a method of recycling polystyrene. Now, there are probably chemists in the room, I imagine, but for those of you who aren't, polystyrene is a very hard to recycle set of polymers. These are some products. There are a lot of foam products, pillows and cushions, right? And there hasn't been a good way, to my knowledge, to recycle these. So you don't put these in the, in your recycling bin outside your home. They typically get thrown away. But these scientists here figured out that you could do a simple end-of-life upcycling of these, polyurethanes, using a room temperature method. You add an organic acid, and basically what you get is I'll let them walk you through it if you're interested, but you basically end up with a super strong adhesive at the end that can be repurposed for industrial applications. So you basically degrade the polyurethane, and turn it into an adhesive and a solvent that are incredibly useful. Okay, and so this is a perfect example of upcycling from something that we couldn't even recycle before. Pretty remarkable discovery. Okay, another example, and this I'm switching gears here now to not research making a difference, but policies making a difference. This is an example that came out last fall this is published in the Washington Post, but it's based on work that was done in the Netherlands. So in the Netherlands, the policymakers have been very committed to reducing climate and other environmental impacts of food production. And what this story was documenting is how the Netherlands, a tiny, tiny country relative to the United States, has become a major exporter of food. And actually, the Netherlands now supplies most of Western Europe with all of its fresh fruits and vegetables, even though it's incredibly tiny. Well, how have they done it? Well, government set policies that incentivized research and development of these techniques. And so the Dutch teams have developed these incredible cell-cultured meat, vertical farming, seed technology, robotics in livestock, all these techniques that have allowed them to focus on decreasing water usage and also reducing carbon and methane emissions while producing more food. So just to give you a sense of the scale of this, the Netherlands provides vegetables to much of Europe, as I said. There's an area of about 24,000 acres. So they're doing this in an area of that tiny country that's about twice the size of Manhattan. So I think the article was trying to make that sound big, but to me that still sounds pretty small for producing so many vegetables, right? And the way they're doing it is that the greenhouses use less fertilizer and water, and they basically use 1/10 of the land that it would take for dryland farming, right? So you can produce as many vegetables. It would take 10 times as much if you were doing traditional farming. And more impressively, perhaps, Dutch farms use only 1/2 gallon of water to grow about a pound of tomatoes. How much do we normally use in typical farming? 28 gallons. So it's like a 50-plus-fold reduction in the amount of water to grow a pound of tomatoes. That's remarkable. And that's the result of policies driving innovation, but I want to emphasize that that is also an innovation in technology that's arising because these scientists and engineers have been incentivized to do this. Speaking of technology, let me go back to that IPCC report that I showed you before, but I'm going to show you a part I didn't mention. These are various kinds of mitigation options that that they suggested at the end of the IPCC report could actually make a difference in reducing carbon. So what the axis is going to be here is, again, gigatons of carbon that could be saved by changes associated with these innovations. And I'm sure you can't read this unless you're eagle-eyed, but up at the top is solar technology, wind technology for energy. There's some efficient buildings and fuel, electric vehicles and things like that here. And the length of the bars that I'm going to reveal in just a moment is how many gigatons of carbon they could save from innovations that we already have, right? That I'm going to reveal now, are gigatons of carbon that we could save from things we already know how to do, all right? So it's not the scale of the bars that I want to focus on here, although that alone is impressive. What I want to focus on is the color of the bars. So this is also color-coded by how much they cost, right? And the redder the bar, the more expensive it is relative to standard practice, the background practice that we use today. But these blue areas are areas that are current, and this is in solar and wind in particular here, and here around fuel-efficient vehicles, electric vehicles and things. These are things where the carbon-saving technology is actually cheaper than the standard practice because of increases in technology, right, in our technical capacity for battery storage and for efficiencies of that kind. Speaking of technology making a difference, I want to switch gears yet again and talk about how our choices can make a difference, picking up on this same report. In the IPCC report, they also talked about the potential for mitigation in particular sectors, and here I want to focus on the potential for mitigation of carbon uptake in the food sector. And this white bar here, you might just be able to make out in the background, shows that we could save 20 gigatons of carbon a year by changes in the food sector, which is nice to know. But the part that I really latched onto was this right here. This is the percentage of those 20 gigatons that are demand-side mitigation strategies, meaning choices that follow from what consumers do, not what producers do. So almost half of the reductions in the food sector could come from choices we make as consumers. And that pattern of a really strong demand-side mitigation was consistent for all the sectors that they looked at, right? Huge reductions just from demand side. And I want to emphasize here that other recent research has shown that you can do these kinds of demand side mitigations without reducing quality of life for people. So this is all stuff we know how to do now. I'll come back to that point. Okay, and last I want to say, in thinking about lessons we could have learned, is that we know that education makes a difference. Now, many of you are educators, and I hope some of you are students, so you know education makes a difference in some way, but I want to point out a very specific example, and this is one that I've worked on. We've developed a science literacy course for college students that we're offering at Bard College where I teach. I'm going to show you a few images of that course, showing people and their professors in the laboratory and in the classroom doing some of this work. And I want to tell you a little bit about it. Essentially, citizen science, as we call it, was designed to teach basic science literacy to all students at Bard College. It's actually required of all students, and they have to take it in their first year. The way that we do it is we have all first-year students come back 2 weeks early from the January break. So they come back 2 weeks early, and they take an intensive course in science literacy during those 2 weeks, and then they're joined by the other students, and the second semester continues. Now, the students are taught in small sections of about 20 students each, and they do a lot of hands-on work in those classes, and all the teachers are PhD-level scientists, right? So a lot of people, when they hear about this course, get excited about the structure, but that's not the part that I'm excited about. I'm not excited about, sort of when the students are there or whatever. I'm excited about what we're teaching them. What we're teaching them, I think, is pretty unique. What we're teaching them is how to focus, how to understand the strengths and weaknesses of experiments, models, and correlations as ways of answering scientific questions. And we really emphasize transferable knowledge. So what can you extract just by the fact that something is an experiment, a model, or a correlation? So that's the first part. And then the second part we're focusing on is how answers to most scientific questions that we actually want answered don't result from one big breakthrough study. they result from the synthesis of lots of studies that are a mix of experiments, models, and correlations. And so we teach them how to look at the strengths and weaknesses of each individual study, and then also how to put them together into a synthetic understanding that addresses a major scientific question, right, or major science and society kind of question. I'll leave it there. So we've just finished a big review of this. I designed the program, but I don't run it. There's a director who runs it, but I was asked to come in and do a review of it, and we've just finished the review. I haven't even shown it to the dean yet, but I figured you might as well see it. So we have a bunch of different assessments, and one of them is a sort of self-assessment, and so I just picked out one of the examples here. For those of you who don't know, BART is not known for its science-philic students. It's a sort of arts and literature-focused school, and we've been building the sciences there, but these students don't come into January thinking this is going to be the greatest experience of their lives. Let me just leave it there. So what these students say is, my ability to describe the nature and importance of science literacy has, and then we're going to give you a Likert-type scale. This is for 2 years, 2019 on the bottom and 2020 on the top. The subsequent years were all impacted by the pandemic, and so we chose to evaluate the ones pre-pandemic just to kind of try to get that baseline when we put into place this curriculum. And this is basically what you get. Basically, almost 90% of these students reported that their understanding of the nature and importance of science literacy had increased moderately to substantially, and this includes the science majors, right? So they felt a gain in science literacy. As I mentioned, we have other assessments, and we actually can see that that's not only that they realize they know something they didn't know, but they can actually do things that they need to know how to do with science literacy around our goals of the course. Okay. So I want to switch gears now from lessons we might take from some of the successes of the last few years and think about what kinds of opportunities there are. And here I want to go back to this graphic that I've shown you a few times now and say, what I've shown you is that these daunting challenges interact. Climate change affects infectious disease, and it also affects biodiversity loss. And of course, biodiversity loss, as I said, can affect emerging infectious diseases. But some of these arrows aren't very well worked out. And in fact, there's room for a lot of research around these very interconnections, right? So I would just point out a couple of arrows that we don't know much about. For example, we don't know very much about how emerging infectious diseases affect climate change. And here we might imagine changes in the activity of people or something like that. We might remember the ways in which our activity around the globe declined during the spring of 2020 and the kinds of responses that the globe showed us in response in return. But here I'm thinking also about emerging infectious diseases, not just of humans, but also, for example, of plants that can cause big changes in global carbon budgets, right? So we don't know much about that really at all. We also don't know that much about how biodiversity loss affects climate change. That's an area where we could know more. And I would say the biggest missing piece is how all three of these interact together. There's one example that I could give you that integrates all three, maybe two if you really stretched it. So this is the interface of these three and how they dynamically interact is actually a pretty profound frontier. Now, I showed you this, and I want to emphasize that research can involve painstaking years of unraveling connections, and it can also involve these kinds of discoveries. And I don't mean to minimize the discovery. I mean to say that they discovered something that was immediately transformative. And here I want to emphasize that the scientists who did this work at UIUC are from two different departments. So I picked up from a distance on the multidisciplinary collaborations that are apparently now a hallmark. It showed to me from a distance that UIUC really does this really quite remarkably, and there are lots of examples of it. And so I want to say that opportunity for all of you, those of you who are here at UIUC, is really profound and different than it is other places. And I think this conference is a fantastic opportunity to launch some new collaborations because we're all in the room together. I also showed you this slide before talking about how technology can make a difference. But I think there's a lot of room for thinking about how policies could incentivize the adoption of these technologies. And we have some policy experts in the room with us for this conference. I had this slide in there already, and then I opened my New York Times this morning, and of course, the EPA has just laid out under the Biden administration a policy that is meant to be a game changer for increasing the adoption of electric vehicles, right? So this is a huge policy decision, It's going to be contested, right? It's already being contested, so it's going to be contested, but it could potentially be transformative. And again, in a single stroke, leading to potentially the adoption of, I think the goal is 75% of vehicles sold in the United States being all electric by 2032. I could have some details wrong. Okay, so there's a lot of research to be done on what kinds of policies can increase the adoption of these practices. We can be looking again, and I showed you this too, we can be looking again for these kinds of win-win solutions, and also potentially win-win-win, meaning biodiversity, carbon, and emerging infectious diseases. So I'm very interested in how restoration and rewilding can potentially mitigate outbreaks of emerging infectious diseases, and I've just gotten funding for that. If anyone's interested in that, I would love to talk to them about the connection between restoration and emerging infectious diseases and how some of these win-wins could potentially be implemented. Before I go on from this slide, though, I do want to emphasize, and I'll come back to this point in just a minute, that we really want to think about this last bit of the quote from the report, that we're trying to be thinking about win-win-wins that meet everyone's aspirations, not just the aspirations of the powerful, the people who are empowered to make decisions or to make profits. And so win-wins are defined by who you're looking at the time, right? Who's winning? So I'll come back to that point. Okay, and on this education stuff, I'm very proud of this work, of what we've developed, and I see it as having a lot of potential. There are some other programs like this around the country, teaching different things, but focusing on college student science literacy and making big gains. One of them is led not far from here by Jenny Dower at the University of Nebraska, and one of the things that Jenny has found at the University of Nebraska is that the efficacy of her version of these kinds of approaches is strongly affected by which socio-scientific issues you put before students. And so we have this interface between the scenarios we give students to explore scientifically and their other belief systems. And when those two things come in strong collision, you can actually have a counterproductive effect on science literacy. And so Jenny's been a pioneer in that kind of work, and we have a lot more to figure out around that kind of education. So that's a major opportunity. We know some things that work, but how do we put them across to the areas where they might matter the most to help students stay open to these, or potentially change the way we teach to address more controversial topics. Okay, so the last opportunity I would put in front of you, and I've hinted at this the whole time, is that it just strikes me that this conference brings together the right people in the right place at the right time. Here we are, all together, face to face, many of us unmasked, and we're going to have this evening and then also tomorrow together at this institution that so prioritizes multidisciplinary collaborations. I mean, I made a list. I wasn't sure who all would be in the room, but I made a list of the departments, the disciplines represented by just the speakers and the organizers. I realize that's a little hard to see down at the bottom, but we've got entomologists, natural resource managers, engineers, microbiologists, medical doctors, veterinary doctors, public health specialists, atmospheric scientists, economists, ecologists, climatologists, anthropologists. It's an incredible diversity of disciplines represented here. I don't think any of you knows everybody else here. If you do, prove it to me, okay? So there's a tremendous opportunity just presented by this conference. All right, and I mentioned that I was going to end with a couple of caveats. The first of these that I've returned to a couple of times is this idea of equity, or to flip it around, inequity, right? And there are a couple of panels tomorrow that are going to address this issue, how do climate change impacts affect people, and how are those impacts felt around the globe, focusing on some of these issues of equity. And there's a panel tomorrow afternoon that I really want to highlight on these issues of equity, right? And the kinds of questions we're talking about here are questions like who gets to ask the question, who gets to define what the research question is, and how should that be determined? And also, as I've alluded to already, who benefits when we have a win-win scenario, for example, and who pays the costs when we have a scenario in which someone is going to pay some kind of cost. And then the last caveat, and then I'll leave you to the reception, or question and answers, maybe. The last one is, look, I'm a researcher, and I suspect many of you are researchers, either currently active researchers or aspiring researchers as students. And I love doing research and answering questions and generating new knowledge. That's why I do it. But I just want to emphasize that it's really easy for me, and I suspect maybe even for one or two of you, to fall into the trap that if I just produce knowledge, that's enough. right? That just the production of knowledge is enough. And so I'm just going to say really clearly, knowledge is not enough. We can know a lot of things, but if we don't translate that knowledge into some kind of action, it's just knowledge, right? And we also need to, speaking to my previous slide, we also need to translate it responsibly. And so I really want us to think while we're here about how we take the knowledge that we've generated and translate it. Now, some people in the room are gifted translators of scientific or technological knowledge, I'm sure. You don't have to be, but you should be thinking about when do we know enough to stop asking the research questions and start focusing on translation, and what role could you play in that process? And then I'll end with a thought from my children, on whom I practice this talk. And that is, that's all well and good, Mom, but keep in mind that in many cases your most effective levers might not be in your professional life, they might actually be in your personal life through your civic opportunities. They're both political science enthusiasts. So I will leave you with that. Fanatics is what was crossing my mind, but still, I'll leave you with that thought, and I'm really looking forward to the reception and the chance to interact with all of you, but I think I have time for a couple of questions as well.